One keys up. I remind you again, please take a look at the questions on this exam, which are indicated as being most commonly missed, because we will revisit a number of these questions with similar questions on exam 2, probably quiz 2, and give you a chance to catch up with the chemistry so far that you need to understand, but as yet have not successfully done. Hey, I understand. This stuff is tough. I didn't make it tough. Chemistry made it tough. And my apologies, but I will have to cancel today's office time because I need to attend a special lecture, which is immediately following this gathering. If you think about what we have considered in chapter 18, you should recognize that we now have assembled all the tools necessary to give us the ability to take any water solution and analyze it in detail so as to determine the concentration of any species in the solution whose existence depends on pH. What are the considerations? Well, of course, we've got to pay attention to the chemistry of the solute. In terms of M sub I, what do we do with this information? With this information, what do we do? You want to analyze any solution? What do you got to do first? What? What? Inventory. You know that? Well, let's just go to QPSI. Because if we're going to get concentrations, then we got to pay attention to this inventory quantitatively. Ka, we got a solute acid. Kb, solute base. You got more than one acid, Ka's for each. Whatever you got. Kw in many cases. In general, in this analysis, what kind of condition exists if we have to pay attention to Kw? The concentration of the solution will be what? Very small. Remember? If you know these things, then you're in business. Material balance as necessary, and charge balance. And if possible, set the charge balance equal to a charge sum. We've talked about cases relating to this, and now I've written a statement. You can equate CB to a charge sum if a system component. You already got that because you will have the inventory done. Can be directly written in terms of M sub I. That's it. Like in the iron nitrate solution, for which we wrote the CB and equated it to a charge sum. Why were we able to do that? Because from our inventory we recognized the presence of nitrate ion. And our understanding of acid-base chemistry allows us to conclude, recognize, that nitrate ion is a species whose existence in solution does or does not depend on pH. Does or does not? Does not. That's why you can set that CB immediately equal to an M sub I value. Because you know the nitrate ion molarity. which means in sum for that solution, You know the total moles of minus charge, total concentration moles of minus charge, 0.030. Remember that? That's the charge sum. That's it. On the other hand, when we looked at something like the ammonium cyanide solution, then you got a problem. Because ammonium ion and cyanide ion react with each other to an appreciable extent, and in so doing become molecules. Ha-ha, that's a problem now. You know the charge balance equation, which we wrote, but you don't know the charge sum. It cannot be written directly from the inventory. You have to analyze the system to know the charge sum. But most often you can set the CB equal to a charge sum. Just look for something in the pot, something in the system that comes from the solute, of course, whose molarity is expressible directly in terms of m sub I. That's it. From that you can write the charge sum. Examples. 10th molar to 2 sig fig sulfuric acid solution, 1 times 10 to the 5 minus 1 times 10 to the minus 5 molar sulfuric acid solution. Let's start by writing the complete system charge balance statement for our water solution of sulfuric acid. Doesn't matter what the molarity is, the complete charge balance statement will always be the same. Right now, do it. You got that? How many got this? Ah, never mind. Hey, we've been through this chemistry. Now we want you to be able to apply it. Can I set this charge balance statement equal to a charge sum? We have 2 different sulfuric acid solutions to consider. 0.10 molar. Can I immediately write the charge sum value for 0.10 molar sulfuric acid solution? Yes or no? I got to vote for yes. What is the charge sum value?
0.10?
Nope. Because the answer is no, I can't do it. Why can I not do it? I have to know the extent to which hydrogen sulfate ion reacts with water to become hydronium ion and sulfate ion in this system. That's the only way I can know the charge sum. Now let's look at the second solution. To assist you in thinking correctly about the second solution, and in realizing why for the second solution, yes, you can write the charge sum value. The second ionization for sulfuric acid solution is the one we just cited, isn't it? Hydrogen sulfate ion plus water, hydronium ion, sulfate ion as products. The extent of this ionization depends on what properties? Molarity? Is that a large molarity? 1 times 10 to the minus 5? And what else? Ka. Is Ka for hydrogen sulfate ion a rather substantial Ka as far as weak acids go? 1.2 times 10 to the minus 2, you're damn right. This is clearly an acid, even though it's weak, which by progressive dilution can ionize to an extent of 100%. Do you think that might apply to this system? You betcha. So what's the charge sum value for the second solution? What is it? I can't hear you. Talk louder. I can't hear you. What is it?
3 times 10 to the minus 4.
3? That's a material maker you got going there. A magic system. I heard it. What is it? Hydronium ion molarity is at least m sub I. At least 1 times 10 to the minus 5. But for this system, the second ionization goes 100%. So the hydronium ion molarity will be twice m sub I, which in that case is equal to the charge sum, because in this system, the only positive thing you got is hydronium ion. And if you don't believe this, that is to say, if you're curious about the legitimacy of our contention that twice m sub I is in fact the charge sum for this system, hey, get out your scratch paper when you're thinking further about this and prove it to yourself. But we've already engaged in the considerations which underlie why this is so. Ki is rather substantial, and m sub I is damn small. That's it. Now then, let's bring all this stuff together with the last general topic to be considered in Chapter 18. How do we get the hydronium ion concentration for a water solution of a solute whose components do affect pH, but find that the principal Bronsted-Lowry acid-base equilibrium in this solution does not involve hydronium ion or hydroxide ion. For example, sodium hydrogen carbonate solution, which I trust you'll recall we talked about earlier on at the start of Chapter 18, when we, for example, examined the acid-base table and recognized the uniqueness of the acid-base chemistry of hydrogen carbonate ion. It is a Bronsted acid, which is stronger than water. It's also a Bronsted base, which is stronger than water. And there are a few other species which also have this property, whose formulas are contained in our acid-base table. Now I remind you, our acid-base table is hardly comprehensive. It just contains some formulas for rather commonly encountered acid-base species in water chemistry, many of which you deal with in laboratory. Here's our principal acid-base equilibrium. If this is the strongest acid, and this is also the strongest base, then the equilibrium of, main equilibrium of consequence in this system has got to be established by this reaction, which gives us these as products. So right off the bat, we recognize you got a problem to get the hydronium ion molarity for this solution, because neither of these things reflect the hydronium ion concentration directly. You got to have an acid-base equilibrium when you got hydronium ion in it or hydroxide ion in it. That's what pH is all about. Now, before we proceed with this, what could you tell me, gee whiz, about the extent of this reaction? I heard a vote for very small. Any supporters for this vote? Good, we got some supporters. Now, as I'm sure you well know, I don't give a damn about votes. But if you can defend the vote, then I'm enamored. Then I'm happy. On what basis would you contend that the extent of this reaction is assuredly small, or at least expected to be small? What is that?
It's a stronger acid. stronger acid.
What's it? I don't like it. I don't know what it is.
The HOCO2.
The bicarb ion reacts and becomes which acid? Which is the product? That's the acid.
CO3.
And what is Ka for HOCO3 minus? It's 4.8 times 10 to minus 11. What's Ka for quote-unquote hydrated CO2, H2CO3? 4.2 times 10 to minus 7. See, I just looked it up. Right. A lot of difference between those values. Right? 4.8 times 10 to minus 11 versus 4.2 times 10 to minus 8. Pardon me. Yeah, 4.2 times 10 to minus 7. Okay. H2CO3 stuff is about 10 to the fourth times stronger, 10,000 times stronger than bicarb. What about the base strength of bicarb versus the base strength of carbonate ion? By what factor do you think they compare? We just told you. About 10,000 times. KB carbonates, 2.1 times 10 to minus 4. KB bicarb, 2.4 times 10 to minus 8. Never mind, you know that I know these numbers. I told you. I've been doing this a long time. You do this like I do this, you'll see the table in your noggin too. So what? But as you know, I don't expect you to memorize this information. I find that to be patently absurd. What you need to do is to understand it and be able to use it. That's what counts. So the extent of this we know is small. But let's look at these reactions. Why should we want to look at these reactions? Do these reactions not involve the principal species? Yes. And the first reaction shows bicarb ion behaving as an acid and giving us a handle on hydronium ion. Whereas the second shows bicarb behaving as a base and giving us a handle on hydroxide ion. In either case, with either of these equilibrium reactions, we got a handle now on pH. And that's the task set before us. Get the hydronium ion concentration. How do the extents of these reactions compare to the extent of this reaction? Compare. Tell me. Reaction extents for those, either one, it doesn't matter. Or you can compare the reaction extents of these to each other and see at a glance that for a given concentration of bicarb ion, the reaction extent of this exceeds the reaction extent of that, does it not? Because this is a bigger K value. And that accounts for why bicarb ion is showing us a solution which is acidic or basic? Basic. Strongly basic? Hell no, that's a damn tiny number. Mildly basic. So how does the extent of this reaction showing bicarb ion reacting with water as a Bronsted base compared to the extent of this reaction, where we see bicarb ion reacting as a Bronsted acid as well as a Bronsted base? If I calculate the K value for this reaction, how must it compare to 2.4 times 10 to minus 8? The possibilities are larger, smaller, the same as, or I don't know.
I don't know.
Well, you're honest. Honesty is a good quality. Now, I'm going to say absolutely, absolutely, without reservation or pause whatsoever, the K value for that reaction has got to be bigger than 2.4 times 10 to minus 8. Why is that true?
Because with the OH minus, you're creating a stronger base than CO2 minus.
I can do that, but I need there's a simpler way to answer this. This reaction with the K value 2.4 times 10 to the minus 8 is a measure of the ability of bicarb ion reacting as an acid or base? Base. Which means in this reaction, water is reacting as an acid. So for this reaction, I'll say the first bicarb is the base bicarb, and the second bicarb is the acid bicarb. Which is the stronger acid, bicarb or water? Which one? Well then, damn it, bicarb is going to extract H plus more effectively than water. It's a stronger acid than water, which guarantees K for this is bigger than K for that. That's it. This is the neat part, the understanding part. Yes?
So it's larger than 2.4 times.
The K for this is bigger than 2.4 times 10 to the minus 8. And calculating this K is easy. If you don't see how to do it immediately, well, some of you should now know how to do it, because some of you got through this in discussion class yesterday. How many of you yesterday looked at the issue of calculating K's for equilibrium systems for which the K is not given, or you can't look it up? Huh? See? Yeah, all right, good. So you know how to do it. At least you should. We'll review that in a moment, because it's important. Back to this. Now, let's look at 1861 and 62 before we get at this part of this puzzle. We recognize this solution is mildly basic. This Kb bicarb is bigger than Ka bicarb, but Kb bicarb by itself is a very small number. That accounts for the mildly part, and the Kb K versus Ka factor accounts for the basic part. Now, why is this a difficult system to succeed in calculating correctly the hydronium ion concentration? Here's the reason why. Hydronium ion concentration and carbonate ion concentrations for this system are not equal, as the H2CO3 quote-unquote molarity is not equal to the hydroxide ion concentration. That means for this system, you can't take this reaction or this reaction and apply x squared over m sub I minus x. Forget that. Why is this true? Notice what this does from an algebra standpoint. It magnifies the number of unknowns. So to solve this puzzle, we got to go to mass balance and charge balance. Not a big deal, since we now have introduced ourselves to these considerations. But why is this true? The answer's on the board. Not on this board. It's on that board. On the bottom of that board. Have we not just argued that the extent of that reaction exceeds the extent of either of these? Well then, guess what? I got this reaction, which is the principal BLAB-EQ in this system, and it makes this stuff, as well as making this stuff. I have this reaction, which is the only source of hydronium ion of consequence in this system, and this reaction, which is the only source of hydroxide ion in this system. But this reaction also makes carbonate. That reaction makes carbonate more effectively. Right? That guarantees the carbonate molarity for this system has got to compare how to the hydronium ion concentration? Got to be bigger. And that reaction, like this reaction, also makes H2CO3, but only this reaction makes hydroxide. This guarantees that the molarity of this must compare how to the molarity of hydroxide. Got to be bigger. See? So we got more unknowns than just X, or whatever the hell you want to call it. All right, a couple more comments on how to proceed. Because the solution for this system is in detail in the notes. I don't intend to take time to rewrite this stuff on the board. But we will discuss some of the considerations necessary which underlie this solution. That's what we're presently doing, and that's what we now continue with. All right? MB. MB right now, right on the paper. It's in the notes, but don't look at the notes. You need to practice. You need to know how to do this. So that on the exams and quizzes, you know how to do this. There's the MB we're concerned with. 0.10 has got to be equal to the sum of the molarities of the various forms of carbonate-containing stuff in the system. You remember from an acid-base standpoint, material balance depends on what? That's stuff you got to know. Otherwise, you don't know what the hell material balance is. Depends on H plus transfer from an acid-base standpoint, right? Well, if bicarb ion, since that's the main pH affecting stuff in this pot, loses H plus, it becomes carbonate. If it gains H plus, it becomes quote-unquote H2CO3. So that sums up the various possible forms of carbonate-containing stuff in the system. So there's the material balance equation with which we are concerned to tackle this. What does this allow us to do? From an algebra standpoint, this allows us to write the molarity of this in terms of these two. Or the molarity of this in terms of these two, or the molarity of this in terms of these two. Blah, blah, and blah. All right, CB, go ahead. Complete species. Somebody wrote this straight away. Can we set this charge balance statement equal to a charge sum directly, straight away? Yes or no? You're damn right. What is the charge sum? What is it? 0.10, please. Let us not throw away significant figures. We agree with this? Isn't that the M sub I value? Is it true that adding the hydronium ion molarity for this solution to the sodium ion molarity is guaranteed not to change the value? Is that true? Have we not determined this solution to be mildly basic, which guarantees the hydronium ion concentration compares how to 1 times 10 to minus 7? Smaller than 1 times 10 to minus 7. If you take something smaller than 1 times 10 to minus 7 and add it to 0.10, you damn sure ain't changing 0.10. Hey, let this stuff talk to us. And that's the hard part for you. You haven't learned how to let this stuff talk to you yet. And you got this crazy guy standing in front of you, jumping up and down saying, let this stuff talk to you. Well, that's what I'm trying to do. Show you how you allow this stuff to talk to you. Because if this stuff doesn't talk to you, you will never understand what it means. And if you don't understand what this means, this is nothing but a big mass jumble that all it does is give you a severe headache and warts. Or whatever. Acme outbreak, I don't know. We don't want any of that stuff. We want understanding. Now then, the remaining part of the puzzle is getting on with the solution. Now we want the hydronium ion concentration. So the way I will tackle these is to start, which is what we've done before for a number of solutions, by putting the hydronium ion concentration in a box, a range. We know the solution is mildly basic. So what is the max possible value for the hydronium ion concentration? A value above which the hydronium ion concentration cannot be 1.0 times 10 to the minus 7. Now, we've also recognized the solution is mildly basic. Pardon me. That's why we wrote this. But as a consequence of the solution being mildly basic, we can calculate hydronium ion concentration min. But calculating hydronium ion concentration min straight away is not quite so simple. But I'll tell you what you can calculate straight away, since we know this system is mildly basic. We can get this. And from this, can we get hydronium ion max? I mean min? If I get this number and take Ka and divide it by this number, I get hydronium ion min. Okay? We're letting this stuff talk to us. How do I get this? I want to be able to get a number. I can't get that number from the charge balance equation. Now then, when I ask this question, I would hope that the first thing, well, I know about the first thing, but the main thing was got to come to your mind when you think about answering this question is, I got all the stuff on the board, all the equations written that I need to consider to solve this puzzle, right? That doesn't have hydronium ion in it, so I can't use that thing. Top one doesn't have hydronium ion in it, I can't use that thing. But the Kb expression's got hydronium ion. Damn it, hydroxide ion. That doesn't have hydroxide ion in it. That doesn't have hydroxide ion in it, but this Kb expression has hydroxide ion in it. And as pointed out, the Cb expression's got hydroxide ion in it. But at a glance, I can look at the Cb expression and know I can't get a handle directly on the molarity for hydroxide ion. But what about the Kb expression? How will I treat the Kb expression to get hydroxide ion max for this system? What will I do? Take the square root of Kb? Not quite. Take the square root of Kb multiplied by what? By what? Yeah. Then I'll apply x squared over m sub I minus x to Kb. I know that's not going to give me the right hydroxide ion concentration, but I know it's got to give me the upper limit value for the hydroxide ion concentration. Because when I apply x squared over m sub I minus x to Kb, I am saying that the molarity of H2CO3 and hydroxide are the same, right? But I know that's not true. I know the molarity of H2CO3 is bigger than the hydroxide ion molarity. Right? So whatever I get from that solution is going to give me a value for H2CO3, which is too small, and a value for hydroxide ion, which is too big. But it'll give me the upper limit value. So hydroxide ion max is this. And now I'll get hydronium ion min, and I got the hydronium ion concentration in a box. Pretty small box. And then when I go about the business of solving, to in fact get the correct hydronium ion concentration for this solution, I'm going to take my hydronium ion max and my hydronium ion min, calculate the pHs for each, add the pHs together, and do what? Divide by 2. Because that's going to give me the halfway hydronium ion molarity between hydronium ion max and hydronium ion min. And then I'm going to put that into these expressions that I have and see if all expressions are satisfied. And when I get the right value for hydronium ion concentration, all these expressions will be satisfied. That's what I'm going to do. And this solution is in detail given to you in the notes. So we'll write that down. From this we get hydronium ion min pH 7.00. You do this, you get the pH, add up the pHs, divide by 2. So I'll write pH max plus pH min over 2 gives me the halfway value for the hydronium ion concentration for the solution. That's what I do. Now, under no circumstances on a in-class quiz or exam would I ever give you something like this. The time for calculation is too long. But I certainly am at liberty to ask you questions which are in regard to what considerations you have to make to solve this puzzle. And that's what we've been talking about. All right? Now then, in wrapping up Chapter 18, let's take this question. Calculate the hydronium ion concentration for ammonium bicarb solution. First, recognize that this solution is comparable to our bicarb solution because in this solution the principal Bronsted Lowry acid-base equilibrium also is not a source of hydronium ion or hydroxide ion. How will the extent of this reaction compare to the extent of this reaction? Do you see at a glance that for this equilibrium, the ammonium ion is behaving as the Bronsted acid, and the bicarb ion behaves as the Bronsted base? So I repeat, how does the equilibrium of this, let's label it as A, compared to this, we'll label that as B. Which one has the larger equilibrium constant, A or B? A. How do you know that?
H4N plus is
Because ammonium ion is a better acid than bicarbonate. Bingo. Now you monkey around with all this other stuff. Let's ask one more question. And we'll finish this up next time. Is this solution going to be mildly acidic or mildly basic? Mildly. How many vote acidic? How many vote basic? Only a couple of right votes. That's not good. This too is mildly basic. But it's not as mildly basic as this other solution. Why is that true? Here, the H plus, principal H plus source is ammonium ion, which is a stronger acid than bicarb, isn't it? But Kb bicarb is still a bigger number than Ka ammonium ion, isn't it? That guarantees this solution is mildly basic. We'll pick it up from this point next time.